we're going to do in this video is we're going to review the idea of oxidation numbers. Now what oxidation numbers are, they're a way for us to describe how electrons are distributed between atoms that are covalently bonded, but the distribution is not necessarily equal. We sometimes call them assumed charges. Because one atom is more electronegative than the other, it will pull electrons towards itself, causing a negative charge on that side of the atom. That will give a little bit of the properties of an ionic bond. So they act like charges. Even though they're sharing, they're acting like a charge. That's why we sometimes call them an assumed charge. Now, there's some basic rules with oxidation numbers. First of all, the oxidation number of any atom is 0. So, if I have a sodium atom, its oxidation number is naturally 0. Same thing if I have a chlorine atom. It has an oxidation number of 0. Another rule is metallic ions always have an oxidation number equal to what is naturally their charge. The sodium ion naturally has a +1 charge. So we say that it naturally has a -1 charge. The copper-2 ion naturally has a +2 charge. So we would say it has an oxidation number of +2. When atoms bond, the more electronegative atom always assumes the negative oxidation state. It always acts like the anion. Because it is stronger, it is more electronegative, it will pull electrons towards itself, causing it to have a negative charge on that end. So, if I have a compound such as water, oxygen is the more electronegative element. So it will take on the negative oxidation state because a partial negative charge will build up on this end of the molecule. While our hydrogen, on the other hand, will take on a positive oxidation state because electrons are being pulled away from it. Alright, and that is because on this end of the molecule we have a partial positive charge. That's what makes this molecule polar, that and its geometry. Okay? Fluorine always has an oxidation number of -1. It keeps that oxidation number because it is the most electronegative element on the periodic table. Oxygen always has an oxidation state of -2. The only exception to that is if it's in a peroxide. If it's in a peroxide, alright, then it will take on a -1 oxidation state. Now, examples of this. Water, for example. Here, oxygen is in its natural state, so it will take on a -2 charge. The oxygen in this compound has a -2 oxidation state. But if we put it into hydrogen peroxide, now that oxygen is taking on a -1 oxidation state. And the reason for that is because this is the peroxide anion. So if it's in peroxide, it's -1. Every other case, oxygen has a -2 charge. Hydrogen is a special case. If hydrogen is attached to a more electronegative element, it will take on an oxidation state of +1. If hydrogen is attached to a less electronegative element, it will take on an oxidation state of -1. Now, an easy way to look at this is, if hydrogen is being used as a metal, it will take on a +1 oxidation state. If hydrogen is being used as a nonmetal, which are typically more electronegative, it will take on a -1 oxidation state. So you just have to look at how hydrogen is being used to determine what kind of oxidation state it will take on. Okay? Now, the sum of all the oxidation numbers for a neutral molecule or formula unit is always 0. So if I have a molecule such as CO2, this is a neutral molecule. The oxidation numbers here have got to add up to be 0. So this is very easy to do because we see that oxygen, this is not a peroxide, this is carbon dioxide. So oxygen in this case takes on a -2 charge. To figure out what carbon is very easy. I have 2 oxygens, each of them with a -2 charge. Now, if I add on 1 carbon, figuring out what its charge is, it's got to be 0. Well, in this case, I get -4 plus the unknown is equal to 0. So the only thing it can be is 4. So in this case, oxygen has a +4 oxidation state. Another example of this is if we come up with a molecule such as, again, H2S. All right, I know that hydrogen in this case is being used as a metal. It is the lesser of the 2 electronegative elements. So it will take on a +1 charge. Sulfur, in response to this then, has got to take on a -2 charge. Because there are 2 hydrogens, each with a +1 charge, plus 1 sulfur with a -2 charge, has got to equal 0. The oxidation states are going to add up to be 0. Now, one thing to understand, elements, even though they may not be oxygen or fluorine, if they are the more electronegative element, they will always take on the oxidation state that is equal to what their natural charge is. Sulfur, in this case, its natural charge is -2 anyway, and it will take on that -2 charge because it is the more electronegative element. Now, oxidation numbers for polyatomic ions have got to add up to equal the charge of the polyatomic. Example of this, SO4 2-. We know that oxygen in this case, since it's not in a peroxide, has got to take on a -2 charge. Well, there's 4 of them, each times a -2, plus 1 sulfur times whatever its charge is, has got to equal -2. Well, this would be -8 plus blank is equal to -2. Well, the only thing that can be then is, this has got to be 6. So in this case, sulfur takes on a +6 oxidation state. Now, we can work this out for pretty much any type of molecule. If we try something like H3PO4. Now, this is easy enough to figure out because we know oxygen is not being used as a peroxide. So oxygen is a -2. Hydrogen is being used as a metal. So it has a +1 oxidation state. Well, we can figure out what the oxidation state for phosphorus is by simply looking at these 2. I know I have 3 hydrogens with a +1, plus 1 phosphorus with an unknown charge, plus 4 oxygens, each of them with a -2 charge, has got to be 0 because it's a neutral molecule. Well, that leaves us with 3 plus the unknown minus 8 has got to be 0. Well, the only thing the phosphorus then can be is 5. So phosphorus is a +5. Now, if I do something like this, Na2O2. Now, if I know a little bit about formulas, I understand that this is sodium peroxide. Since I'm dealing with a peroxide, that means oxygen here has a -1 charge. This is a special case for oxygen. Now, in response to that, what is the charge on sodium? Well, I have 2 oxygens, each of them with a -1 charge, plus 2 sodiums with an unknown charge, have got to equal 0. So -2 plus 2 times the unknown has got to be 0. Well, to get this to work out, the unknown charge is a +1. So in this case, sodium has a +1 oxidation state. This is very simply how we do oxidation numbers.